In the following sections, we will explore position vectors, force vectors directed along a line, and using the dot product. The objectives for these sections are that you should be able to 1. Represent a position vector in Cartesian coordinate form from the given geometry, 2. Represent a force vector directed along a line, 3. Use the dot product to determine an angle between two vectors, and 4. Use the dot product to determine the projection of a vector along a specified line. The applications of determining the magnitude of a force along a line, as well as the angle at which that line is occurring. In particular, there's the need for a precise spatial representation, meaning that you need to model forces, for instance, on a ship. So if we look at this mooring or the docking system here, you would want to know what are the forces acting on that ship, and you have the tension associated with the wind or the current or the tide that is moving and causing tension within that line. Similarly, you would want to break that into components or your Cartesian components. And so you would need to know the angle at which it is occurring. But it is entirely possible that you have only the docking point X, Y, and Z or three-dimensional coordinates, as well as where it connects to the ship. So you can use some of the techniques that we're about to talk about to determine the force along that mooring line. When we do this type of analysis, it helps us with the safety and stability. So understanding the vector property will help you to prevent overloading. It'll ensure balanced tension. And also, once again, you can design for extreme conditions like storms or even high traffic. This also allows us to automate and simulate. So nowadays, ports and ship design is modern. It's done or accomplished using computer simulations. Knowing how your force is calculated by knowing the coordinate system or points along the coordinate system allows you to feed that into a computer simulation. And you can support then autonomous ship systems, dynamic positioning, things like that. And of course, you do need to be able to speak to other engineers about this. And the way you do that is by using correct terminology, which in this case is a force along the line in its Cartesian coordinates. You can also use this, for instance, if you look at this awning, you have three chains holding up the awning. And so knowing where those chains intersect is one application. And you need to do this because that's how you ensure your structural stability. So each chain is going to contribute to holding that awning in place, but you want to make sure that the load is evenly distributed, because if you overload a single chain, you could lead to failure under wind or rain or other loading events. It also helps you to select materials, and that's part of the design. So, what type of chain has the right tensile strength, where exactly you should design your anchor points. You want to avoid different things like sagging or too much tension in your awning. So, you can use this type of technique to accomplish that, which also helps with your safety and risk management. So, you can keep the chain from snapping or the awning from collapsing. So it also helps you with the maintenance. You can actually go and analyze instead of design. So remember that analyze is the other side of design. And so it'll help you to set your inspection criteria and maybe identify any wear and tear. And so if we know where any physical locations are in a three-dimensional space, along those cable ends, or even, as I said, the mooring line, then you can calculate the angle between the cables at any common anchor. You can also use the techniques that we're going to go over to determine, for instance, if you apply a force to a wrench, what portion of that force is going to contribute to actually turning the bolt. A position vector is defined as a vector that tells us where a point in space is, but relative to another point. Now, that other point could be the origin, so it could be the intersection of the xy or xyz plane, or it could be some other point that may be associated with another vector. So let's suppose we have 2 points. In this case, we're going to call those 2 points A and B. And again, we're looking at a 3-dimensional space. Let's say that A has a coordinates XA, YA, ZA, and B has a coordinates XB, YB, and ZB. So if we want to know the position vector, in this case, that position vector would be given by R, or the vector R, then it's the same thing as saying what vectors would, or what pathway should we follow from A to get to B. In this case, along the x-axis, we would have to change our position some distance xb minus xa. Then, once we reach that point, we'd have to change our position along the y-axis some distance yb minus ya. Then finally, we would have to change our position along the z-axis some distance zb minus za. Therefore, the position vector that is directed from A to B, and we'll just call that R, meaning the resultant sub AB, is defined by xb minus xa, and this quantity is times your I vector, plus yb minus ya, where that quantity is times your j vector, plus zb minus za, where that quantity is times your k vector. So try to keep this in mind as you're doing the position vector, that even though A is your starting point and B is your ending point, B is considered your tip. Okay? And so when you're looking at a position vector, you should always subtract your tail coordinates, in this case A coordinates, from your tip coordinates, in this case B coordinates. If a force is directed along a line, then we can represent the force vector in Cartesian coordinates by using a unit vector and the force's magnitude. In order to do this, we must first find the position vector RAB along 2 points on that line. Secondly, we should find the unit vector describing the line's direction. In this case, the unit vector UAB is equal to the position vector RAB divided by the magnitude of the position vector RAB. Finally, we multiply the unit vector by the magnitude of the force. So the force vector is equal to the magnitude of the force times the unit vector UAB. In statics, the dot product can be used to find the angle between 2 lines or the components of a force parallel and perpendicular to a line. The dot product of vectors A and B is defined as A dot B is equal to A times B times cosine theta. The angle theta is the smallest angle between the 2 vectors and is always in the range of 0 degrees to 180 degrees. The dot product has the following characteristics. The result of the dot product is always a scalar. That's either a positive or a negative number. Secondly, the units of the dot product will be the product of the units of the A and B vectors. For instance, if A and B have units of meters, then the dot product will have units of meters squared. By definition, A dot B is equal to A times B times cosine of theta. Therefore, when you are taking the dot product of 2 unit vectors, for instance, I dot j, since they have an angle between them of 90 degrees and the cosine of 90 degrees is equal to 0, unit vector I dot unit vector j is equal to 0. However, when the angle between the 2 unit vectors is equal to 0, the cosine of 0 is equal to 1. Therefore, I dot I is equal to 1 times the cosine of 0, or 1. Therefore, it follows that vector A dot vector B is equal to a sub x times the unit vector I plus a sub y times the unit vector j plus a sub z times the unit vector k dot b sub x times the unit vector I plus b sub y times the unit vector j plus b sub z times the unit vector k. Since I dot I is equal to 1, but I dot j or I dot k is equal to 0, we can see that any time a unit vector does not dot itself, it becomes 0. Therefore, vector A dot vector B is equal to a sub x b sub x plus a sub y b sub y plus a sub z b sub z. Dot product is useful for two situations. The first application is to find the angle formed between two vectors or intersecting lines. And the second application is to find the components of a vector parallel and or perpendicular to a line. In this case, for two vectors, A and B, step 1 is to find the dot product A dot B, which is equal to AXBX plus AYBY plus AZBZ. Next, find the magnitudes of A and B. Finally, using the definition of the dot product that we previously looked at, solve for theta, such that theta is equal to the inverse cosine of vector A dot vector B divided by the magnitudes of A times B. Keep in mind, theta should be between 0 and 180 degrees. You can use the dot product to determine the projection of a vector. So suppose you have a vector A. A can be resolved into its parallel and perpendicular components. In this case, we'll call the parallel component vector A sub A and the perpendicular component vector A perpendicular. In order to do this, you would first find the unit vector for A. That is vector u sub A along line AA. Line AA is a user-defined axis along which you are interested in the parallel vector. Next, to find the scalar projection of the vector A along line AA, you would algebraically solve for the magnitude of A parallel, or A sub A magnitude, which is equal to the vector A dot the vector u sub A, which is equal to AXUX plus AYUY plus AZUZ. If instead you want to write the projection as a vector, A parallel, then you take the magnitude that you just calculated and multiply it by the unit vector u sub A. If instead you are interested in the perpendicular component, then you simply apply Pythagorean theorem such that vector A is equal to the square root of A perpendicular squared plus A parallel squared and solve for A perpendicular. Similarly, the vector A perpendicular is equal to the vector A minus the vector A parallel. I'm going to be working 2-101 in the 15th edition of Hibbeler. This problem requires that we find the position of x, y, and of course 0 for cable BA such that the resultant force exerted on that pole is along the axis from B to O. We also want to know what the magnitude of that resultant force is. So the two things that we're looking for is the BA force and the positions, which is x and y, and of course z is 0, and then also the magnitude of the resultant force that's occurring along this pole here at 4 meters. To begin, I'm going to write the equations and the assumptions, and let's first start with a force diagram. On our force diagram, we have our three connections moored at A, C, and D, and then we have them intersected at B. So we first have our F1 from B to D at 350 newtons. Then we have F2 from B to C at 250 newtons. And then we have F3 from B to A at 300 newtons. We have the distances along the x-axis of D. So the y component would be 0, and the x component would be -3, for instance. We know where C is located, but we don't know where A is located. Also, keep in mind these forces that we've been given are magnitudes. They are not the vectors, so we will have to calculate the vector. We will first calculate the position vector, and remember that the position vector is given by subtracting the tip from the tail. So this, generically speaking, that would be xb minus xa, the component in the I direction, plus yb minus ya, the component in the uh, j direction, plus zb minus za times a component in the k direction. This is just the generic formulation. We will, of course, rewrite it in terms of your xd and xa and xc. Next, to calculate a vector f, in this case, I'm going to write the equation for the resultant vector. That is equal to the magnitude of that vector times the ratio of the position vector to the magnitude of the position vector. Finally, the magnitude of a vector is equal to the square root of the components of the vector in the xyz direction squared. Since our resultant vector is equal to the sum of the other three vectors combined, then we need to calculate vector f1, vector f2, and vector f3. To calculate those two vectors, we first need to calculate the position vector associated with each one of the forces in the connecting wires. Then we also need to take the square root of the sum of the components squared so that we can have the magnitude of the position vector. So we'll start with the position vector r1. Since we know the coordinates of D, which is -3, 0, and 0, and we know the coordinates for B, which is 0, 0, and 4, then we can easily find the position vector for F1 as -3 minus 0 for the I component, 0 minus 0 for the J component, and 0 minus 4 for the K component. Keeping in mind, this is the tip minus the tail. So that is equal to xd minus xb plus yd minus yb plus zd minus za. Next, the magnitude of R1 is then xd minus xa squared plus yd minus yb squared plus zd minus zb squared, the square root of the sum. That means that the magnitude of the position vector 1 is equal to 5 meters. Finally, the vector form of F1 is equal to the magnitude of F1 times the ratio of our position vector R1 divided by the magnitude of R1. That is equal to 350 newtons times -3i minus 4k, the quantity, times m, divided by 5 meters. This gives us a vector for F1 of -210i minus 28k meters. We're going to do the same thing for our second force, F2. We first need to find the position vector R2. and that is in the I direction, xc minus xb, plus in the j direction, yc minus yb, plus in the z direction, zc minus zb. And so that is equivalent to 2 minus 0, I, plus negative 3 minus 0, j, plus 0 minus 4k. Similarly, we want the magnitude of the position vector, and that is the square root of xc minus xb squared plus yc minus yb squared plus zc minus zb squared. Finally, to find the vector f, we multiply the magnitude of F2, which we're given as 250 newtons, times the ratio of the position vector divided by the magnitude of the position vector. So we have 250 newtons times 2i minus 3j minus 4k divided by 5.38516 meters. Therefore, we can then write F2 in its vector format. The vector format is equal to 92.85i minus 139.27j minus 185.7k. All this is in meters. Once again, we'll do this for the third force. However, the third force, we don't know what XA and YA is. We do know ZA is 0. So the position vector R3 is equal to XA minus XBI plus YA minus YBJ plus ZA minus ZBK. Therefore, XA minus 0I plus YA minus 0J plus 0 minus 4K. Next, the magnitude is equal to the square root of XA minus 0 squared plus YA minus 0 squared plus 0 minus 4 squared, or the square root of 16 plus XA squared plus YA squared. Finally, we can represent F3 in its vector form by multiplying the magnitude of F3, which is given as 300 newtons, times the ratio of the position vector by the position vector magnitude. That is 300 newtons times XAI plus YAJ minus 4K divided by the square root of 16 plus XA squared plus YA squared. Because we are interested in the resultant force, we will also do this for a force whose tip is at O and tail is at B. Therefore, the position vector for a resultant is equal to XO minus XB I plus YO minus YBJ plus ZO minus ZBK, or 0 minus 0i plus 0 minus 0j plus 0 minus 4k meters. The magnitude of that position vector is the square root of 0 minus 0 squared plus 0 minus 0 squared plus 0 minus 4 squared, which is equal to 4 meters. Finally, the resultant force vector is equal to the magnitude of the resultant force times the ratio of the position vector divided by the magnitude of the position vector. Therefore, the vector FR is equal to negative magnitude of the resultant force times K. Keeping in mind again that the resultant force is equal to F1 plus F2 plus F3, we can substitute each one of the equations that we just derived into our equation for the resultant force. That is, the resultant force is equal to negative magnitude of the resultant force times K. On the right-hand side, F1 is equal to negative 210 or 210i minus 280k, plus our F2 is equal to 92.85i minus 139.27j minus 185.7k, plus our third vector, which is equal to 300 times the quantity of XAI plus YAJ minus 4K divided by 16 plus xa squared plus ya squared, the square root of the sum. To make this simpler to solve, we'll combine our like terms, meaning we'll combine the i's, combine the j's, and combine the k's. So on the left-hand side, again, you have negative frk. That is equal to the I terms, or negative 117.15 plus 300 times xa divided by the square root of 16 plus xa squared plus ya squared times I. Then you have the j component, so plus negative 139.27 plus 300 times y divided by 16 plus xa squared plus ya squared, the square root thereof, times j, plus the k component, which is negative 465.7 plus negative 1,200 divided by the square root of 16 plus xa squared plus ya squared. Solving for each Cartesian component, we start with I. On the left-hand side of our original equation, there is no I component. Therefore, we start with 0 on the left-hand side, equals, on the right-hand side, we already have that negative 117.15 plus 300 xa divided by the square root of 16 plus xa squared plus ya squared. So that we can solve or solve this down to the minimum, then we can divide both sides by negative 117.5, and we can also multiply 16 plus xa squared plus ya squared to the square root. This will give us 0 equals the square root of 16 plus xa squared plus ya squared plus 300 xa divided by negative 117.5. Next, we solve for our y component. On the left-hand side, there's no j component, therefore we have 0. On the right-hand side, we have this is equal to negative 139.27 plus 300 times ya divided by the square root of 16 plus xa squared plus ya squared, and this is multiplied by j. So that we can again minimize this down, we're going to divide by negative 139.27 and multiply by the square root of 16 plus ya squared plus xa squared. That gives us 0 equals 16 plus xa squared plus ya squared to the power of 1/2 plus 300 ya divided by negative 139.27. I'm going to simultaneously solve these equations by subtracting the second equation from the first equation. When I do that, I get 0 equals 16 plus xa squared plus ya squared to the power of 1/2 minus the same gives me 0, then minus 300 xa over 117.15 plus 300 ya over 139.27. When I calculate this, I get 0 equals 0 minus 2.5608 xa plus 2.15407 ya. Then I can solve in terms of xa, or xa in terms of ya, and xa is equal to 0.84117 ya. Next, I substitute that into my first equation, and I can solve for ya. Substituting in gives me 0 equals the square root of 16 plus 0.84117 ya squared plus ya squared minus 2.5608 times 0.84117 ya. Then I want to gather my like terms, and I have 0 equals the square root of 16 plus 1.7076 ya squared minus 2.5407 ya. Kaya. To make this easier to visualize, I'm going to move my ya component to the left-hand side. So I have 2.51407 YA is equal to 16 plus 1.7076 YA to the power of 1/2. Then squaring both sides, I can cancel my square root, and I'm left with 4.64 YA squared equals 16 plus 1.7076 YA squared. You'll notice I left the square off previously. Then, gathering my YA squared on one side, I have 2.9324 YA squared equals 16. Therefore, YA squared equals 5.456. And YA equals 2.34. Now I can take that 2.34 and substitute that back into my previous equation that had XA in terms of YA. Therefore, XA is equal to 0.84117 times 2.34 meters, or 1.96 meters. Notice that there's no I or J component associated with the magnitude of FR. Instead, all of the magnitude of FR is associated with the K component only. Therefore, when we solve for the K component, this is when we can calculate our magnitude of our resultant force. So we have negative magnitude of F, or resultant force F, times K is equal to negative 465.7 plus negative 1,200 divided by the square root of 16 plus XA squared plus YA squared, which we know now, times K. We're going to go ahead and divide through by a negative so that everything's positive, and we're also going to cancel our K's. Therefore, the magnitude of our resultant force is equal to 465.7 plus 1,200 divided by the square root of 16 plus XA squared, or 1.96 meters squared, plus YA squared, or 2.34 meters squared. Therefore, the magnitude of our resultant force is equal to 704 newtons.